So we stopped 2 weeks ago by proving that PC of Q, so the critical value for the random cluster model was equal to square root of Q over 1 plus square root of Q. So I told you that I will not prove this theorem, even though I will give you almost a proof, in fact, for Q smaller or equal to 3. But before that, this will be by the end of this lecture, or maybe even beginning of the next one. Before that, I want to give you at least a hint that this is a natural value for the random cluster model, that there is something special happening at this value. And this hint will come from something very specific to the planar model, which is self-duality. So how do we do that? So imagine that you have a graph G, a subgraph of Z2, and define the following graph. So take Z2 star. I already, I think, mentioned this graph. It's the dual of the square lattice. So you put a vertex in the middle of every face, and you put edges connecting nearest neighbors of this thing. So it gives you a dual graph. And define G star to be the dual of the graph G, and it's going to be defined like that. The set of edges is going to be the set of dual edges corresponding to edges of the original graph. So you see every edge of my primal graph is related to an edge of the dual graph. So if the first one is called E, I will call the dual graph E star. It's the only edge of Z2 star that intersect my edge in the middle. And so what I do, I take all the edges of G, and I take the dual of these edges. It gives me a set of dual edges. And then V star is just the set of endpoints of edges in E star. Okay, so I get a dual graph like that. We try to write a little bit smaller today because we won't have 2 boards. And now, for any configuration omega on 0, 1 to the E of G, so any percolation configuration on my graph G, I can associate a dual configuration, which is going to be defined on the dual graph, such that, in such a way, that we have the following. The value at E star is equal to 1 minus the value, for the dual configuration, the value at E star is equal to 1 minus the value at E. So that exactly means, in words, that the dual edge is closed if the primal edge is open, and vice versa. So now, we saw this already for percolation, and that was, we saw that, well, there is a distribution. This random percolation configuration on the dual graph is simply percolation with parameter 1 minus p, and this is obvious. Well, there is a property for the random cluster model that says the same thing for q bigger than 0 and p in 0, 1. And even if I take boundary condition xi, then if omega is sampled according to a random cluster model on G with parameter pq and with boundary condition xi, then the dual configuration is going to also be a random cluster measure, this time, of course, on G star, with parameter p star and q star. So a priori, the parameters are not the same. And with boundary condition xi star, so xi star is the boundary condition that you obtain from xi by taking the dual configuration of xi. Okay, so you had a configuration. Imagine xi is a configuration outside my graph. It induces a boundary condition. Take the dual of this configuration. It induces a dual, a boundary condition on the dual graph, and that's xi star. So then I need to tell you what p star and q star are, where, well, q star, it's very simple. It's just q, so the cluster weight doesn't evolve. And p star satisfies the following relation. which is p star times p divided by 1 minus p star times 1 minus p is equal to q. So this is the statement. I'm not going to prove it, but in fact it's very simple. Somehow, I mean, let me just sketch how you would do it. Well, what is the number of open edges of omega? Well, it's exactly the number of closed edges of omega star. Okay? The number of closed edges of omega is the number of open edges of omega star. Now the number of clusters of omega, or omega psi, say. What is it? Well, it is, if you think about it, the number of faces of the dual configuration. And so on. So you can relate all the quantities that are involved in this quantity. You agree that the probability of omega star is just this quantity. But this quantity is written in terms of these things, which you can write in terms of these things. And then what do? Well, this quantity is not exactly what we want. You use Euler formula, to write this in terms of the number of open edges, the number of closed edges, and the number of clusters of the dual configuration. So this plus Euler formula, and you do a few manipulations, and you manage to rewrite these things in terms of open edges, closed edges, and number of clusters of the dual configuration. And you just check that, well, it's exactly what you would get if you would take the random cluster thing. So there is nothing here. It's really this Euler formula that is important. Okay? And now what remains is just that, it remains to check exactly how are you going to prove that PC is equal to this thing. First, you are going to notice that this square root of q over 1 plus square root of q is the only point for which p is equal to p star. Okay, so square root of q over 1 plus square root of q is a unique p such that p star is equal to p. By the way, you check that for q equal 1, you get p star equal 1 minus p, which is coherent with the Bernoulli case. So this is a self-dual point, exactly like 1/2 was a self-dual point for percolation. And then, well, the proof that you did for percolation is going to basically, the strategy is the same. So what you're going to first do, you are going to prove that at the self-dual point, you cannot have an infinite cluster. And this is going to be basically Zhang argument, the argument that we described for Bernoulli percolation, that if you have an infinite cluster, you have one in the dual, and then you can construct with positive probability. You can just do something that you will have two infinite clusters. And if you check the proof that I did for Bernoulli, basically it was using only translational invariance. At some point I use independence, but this independence can be replaced by just the finite energy properties, the fact that whatever, if I condition on everything except the state of the edge, it still has a positive probability of being open. So you can check that the proof goes mutatis mutandis, there is nothing to change, and this gives you, for instance, that PC is larger or equal to this self-dual value. For the other direction, you need to prove exponential decay. And this is not easy. For Bernoulli percolation, we had a very simple way of doing it. But for random cluster model, it's a very difficult problem. It is the main problem in the proof. And we can do it. We managed to prove this thing, but this will be too long to present in this class. Okay? So the exponential decay allows to prove the other inequality. Very well. So let me now focus. It's the 6th or 7th part. Let me focus now on the next step. What was the next step is to try to understand what is happening at the critical point, right? And we saw that for Bernoulli percolation, the study is basically based on the Rousseau-Seymour-Welch theory. So the question is, do we have an equivalent of that, of the Rousseau-Seymour-Welch theory, for random cluster models? And the story is a little bit more complicated there. So I will spend just a little bit. I mean, I will basically go too fast on this thing, but if we want to proceed to other things, I won't have time. I mean, I cannot afford to spend too much time on this thing. But let me tell you a little bit what is happening. So what is happening is that there is, I mean, it's not true that you always have the Rousseau-Seymour-Welch theory at criticality for the random cluster model. It will depend on the values of Q. So we are going to see that today. But one thing that is not going to depend on the value of Q is the fact that there are different ways of describing what we call a continuous phase transition. I told you one, I gave you the definition in the first class, which was that at criticality, there is no spontaneous magnetization or no strictly, I mean, the order parameter is 0, something like that. So this is the most natural definition of a continuous phase transition, is to say, for instance, in the case of the random cluster model, to say that if I take at PC the probability of having an infinite cluster going to 0, say, well, this thing is 0. This would be the main, I mean, the basic definition of continuous phase transition. But physicists may disagree with this point of view, and rightfully, in the sense that some physicists will tell you, no, I mean, a continuous phase transition is rather when there is a unique infinite volume measure. You cannot have coexistence of different states at criticality. So this, remember I told you that the extremal infinite volume measure was the free and the wired boundary condition. So if they are equal, there is a unique infinite volume measure. So this could be an alternative definition of a continuous phase transition. There is a third definition, which is that, I mean, the limit, or say the expected size of the cluster at 0, cluster of 0, sorry. So this is exactly, if you think about it, the expected size of the cluster at 0. This thing is infinite. That's called divergence of the susceptibility at criticality. Some physicists will tell you this is the right definition because this is related to the derivative of the free energy. And so if it's infinite, it means that the thing has a continuous phase transition. There is a fourth definition that other physicists would like to see in this case, is that at criticality, if I look at the log of the probability that 0 is connected to the boundary of a box, so being connected to distance n, I look at the rate of exponential decay of this. Well, at criticality, it's 0, meaning it doesn't decay exponentially fast. This is another definition of a continuous phase transition. And there is a last definition, more geometrical, and that will be the one that is the most useful to us, is exactly this Rousseau-Seymour-Welch thing. So it's going to say for every alpha positive and every, there exists, a constant that depends only on alpha, such that whatever the size n, and whatever the boundary condition psi, if I look at the following, so imagine I have a big box like that, and I take a box of size n times alpha n inside. Okay? But let's just say that here, this big box is of size, is distance of size m from the small box. Okay? Well, what the Rousseau-Seymour-Welch is going to say here is that the probability of having an open path from left to right in this case is going to always be bounded from below by C of alpha and always bounded from above by 1 minus C. So what does it mean? If you forget about the boundary condition, about the big box, this is exactly the statement for Rousseau-Seymour-Welch, that you cross a rectangle, whatever the aspect ratio, you cross it with probability bounded away from 0 and 1, and this bound is just depending on the aspect ratio alpha. But here what I want to add is really that, of course, I'm at PCQ. I'm going to add that I put whatever boundary condition psi on this big box. So remember that the boundary condition a priori is changing a lot the measure inside my graph. So I don't want just to take somehow the infinite volume measure and just say I look if I cross or not a box. No, I want to look if I cross or not a box, knowing that I have some arbitrary boundary condition on the boundary here. And remember, for instance, if you take 3 boundary conditions here, the measure a priori is much smaller than the measure you will obtain if you would be directly in infinite volume measure, in infinite volume. Okay? Because the boundary condition, even the 0 boundary condition at infinity, are much bigger than the 0 boundary condition really on a graph which is not far from you. Okay? So here there is uniformity in the aspect ratio, in the size, and in the boundary condition. This is the right generalization of what would happen for the critical Bernoulli percolation. So this is a theorem now, which, what does the theorem say? That for every q larger or equal to 1, all these conditions are equivalent. So if I have one of them, I have all of them. So basically, these different ways of looking at a continuous phase transition, they are equivalent. And if you think about it, it's not very difficult to see that, it requires a little bit of skill, but if you are used to the model, you will easily see that this is the weakest condition, this exponential decay. For instance, this one obviously implies this one, for instance. You can easily check that if this is infinite, of course, this quantity doesn't decay exponentially fast. But it would, if this would decay exponentially fast, this would decay exponentially fast. Okay? So you can see that this implies this. In fact, this, you can check that it implies this by some classical argument. If you have no infinite cluster, you can start to guess that the wired boundary condition at infinity will not change much compared to the free boundary condition at infinity, because the only way somehow you can remember the boundary condition is if you have a path that is going up to there. So if you don't have an infinite cluster, you are not going to see the difference. So these two are, in fact, actually very easily equivalent. So this is the weakest one, and this is by far the strongest one. This one implies all the others very easily. But on the other hand, this one is the one that is going to allow you to prove whatever you want at criticality. Everything you could do with the Rousseau-Semmelweis theorem for Bernoulli percolation, you can do it here with this one. But what I want to do is somehow to highlight just quickly why the boundary conditions are so important, why you want uniformity in boundary conditions. And then we will jump to another representation. So just historically, so this was proved for Q equal 1 first, for Bernoulli percolation. This is it goes back basically to Rousseau-Semmelweis and their co-authors. For Q equal 2, remember that the random cluster model is related to the Ising model. So there, somehow, there is something strange that happened, is that these things were first proved for the Ising model. The equivalent of these properties for the Ising model. And then, by the coupling between the Ising model and the random cluster model, you would deduce them for the random cluster model. So, for instance, these two are basically consequences of Onsager original work. These two are consequences of this, plus the fact that you have what we call Simon's inequality, which we will see on Friday. And this one was proved recently, in fact, by Clément Anglais, Pierre Nolin in the room, and myself. But using specific techniques that work only for Q equal 2, so that are not transferable. And for Q very large, you will see that, in fact, none of the properties are satisfied. Okay? Be careful that I say they are equivalent. I never say that they were satisfied. So for Q large, I will prove in 20 minutes that none of them are satisfied. So this theorem is a theorem by myself, Tassion, and Sidoravicius from this year. It's already 2 years old, but we are very slow at writing it. So, if you want to have it, I mean, we have a good draft now, but it's still not online. Okay, so let me just give you one example, which I think is a good example of why boundary conditions are important. Uniformity in boundary conditions are important. So the first observation is, so let me say corollary. I want to prove that there exists epsilon such that for every n, if I look at the probability, so here I'm assuming 1 to 5 are satisfied. Okay? So I take a value of Q for which these things are satisfied, and I want to prove that the probability of being connected to distance m, well, it decays polynomially. So it's smaller than 1 over n to the epsilon. It's larger than epsilon over n. So you see a very different behavior than, I mean, supercritical, you know it doesn't even go to 0, this quantity. Subcritical, you know it decays exponentially fast. I mean, you expect to decay exponentially fast. But at criticality, you see something different, it decays polynomially fast. So let me try to prove that. So first thing is, well, since you have these things, if you have a path, say you take 2n times n. If you have a path which is crossing a box like that, then one of the points in the middle is connected to distance n. So the union bound is just telling you that the probability of this thing is smaller than the sum over the guys in the middle. There are n people like that. N times the probability, let's put it on here, that 0 is connected to the boundary of the box. Okay? Since this is bounded from below by a C of 2, okay, I get the lower bound. So the lower bound is very easy to get, no problem there. Now, how do you get the upper bound? Well, first observation, what is the probability if I give you a box of size, say, 2 to the k and a box of size 2 to the k plus 1? What is the probability that I find a dual path like that, blocking, surrounding the inner box? Well, what you can do is you can draw the following. You can draw 4 rectangles like that. One here, one here, one here, and one here. And ask that in any of these rectangles you have a crossing in the long direction. Right? If you do this, then the 4 crossings together will contain a circuit surrounding the inner box. But now, for every of these boxes, if you think about it, for a second, here you have maybe epsilon n. This is, say, epsilon n. And this is alpha times epsilon n. So it's exactly of the following form for some alpha. I'm not going to tell you exactly which one. But that means that the probability of having a path like that doesn't go to 0. Okay, there is a bound, there is a constant. It's bounded from 0. And by the FKG, so it means that having that is larger than a constant. And by the FKG inequality, since I need this 4 times, I will just get that the probability of this is going to be bigger than this constant, so something like alpha over epsilon, to the 4. Okay, for some alpha and epsilon that I don't want, I mean, maybe epsilon is, you can put 1/4 or something like that, and then alpha something like 10. But notice that I can put whatever boundary condition here or here, because I can put whatever boundary condition here, right? So whatever the boundary condition psi, I can find a circuit like that surrounding the inner box. And this is the same for the dual because, well, the dual model is also a percolation, a random cluster model with parameter PC. So now how do I do to bound the probability at PC and at Q of having 0 connected to the boundary of the box? Well, let's call this event, let's call it EK. Okay, the event that there is a dual path, say, surrounding the box in the annulus between scale 2 to the k and scale 2 to the k plus 1. If I want 0 to be connected to distance n, I need all these events not to occur. Because if any of these events, so I have this inner boxes like that, if in one of these annuli, I find a dual path, then I'm done. I don't have a path from the inner side to the outer side. Yes? So this is definitely smaller than the probability of the intersection of the complement of EK for all the scales which are smaller than n. So now here what I can do, I can say, okay, this is phi PC Q of epsilon 0 complement times 5 PC Q of epsilon 1 complement knowing epsilon 0 complement, and so on. Okay? So remember now, if I condition, so this first guy, that's exactly what I notice here, not having that is smaller than 1 minus c. Now let's look at this guy. So I'm conditioning on this event not to occur. So this event not to occur tells me here maybe inside something very bad happened for me. So remember I want a dual pass. Maybe here what happened is that everybody was dual open. So everybody is red. I lost my red. Okay. Here. Everybody is red. So this is helping me a lot somehow to have a dual open pass, right? To have red, because as we say, we have the FKG inequality, so everybody is helping each other. But what I say that whatever the boundary condition, this probability is still not too big. Not too small, sorry. So this is telling me that even with this conditioning, by the Markov property and the comparison between boundary conditions, or just a Markov property, it's going to induce some boundary conditions, but they cannot help too much this event. And the probability is going to still be smaller than 1 minus c. And notice that if I don't have the uniformity in boundary conditions, this could be completely wrong. It could be that the first event not having a dual path in the dual circuit in the first annulus is very tough, and the probability is small. But maybe then, once I have this, it's very easy to have in other annulus circuits. So you really want something which is uniform to tell you, no, that's not what is happening. It's always difficult to get this event. So for every of the annuli, I will get a factor 1 minus c. And so since I have roughly a log n annuli, I'm going to get something like n to the minus, something like log 1 minus c over log. So it's going to be a plus log 1 minus c over log 2. So this is going to be my epsilon. Okay? So here I really want to highlight the fact that why is it important to have this uniformity in boundary condition? Because when you use Rousseau-Seymour Welch, usually you are going to condition on what is happening somewhere else, and you want to know that even if you condition, you still have Rousseau-Seymour Welch in the box somehow. And this is going to be induced by the fact that, well, it gives you some boundary condition, whatever boundary condition, but my bonds are uniform in the boundary conditions. So now you will have to trust me on the fact that with this theorem you can prove a lot of things. So basically you get to a level of understanding of the phase transition, which is, I'm stretching a little bit, but basically equivalent to what happens for Bernoulli percolation on Z2. Meaning you know a lot, but you don't know what we call conformal invariance. I'm stretching a little bit because we have additional difficulties. We don't really manage to do it, but I'm going to say something like probably in finite time we will manage to have the same understanding. That's really the main tool. Okay, so this is our theorem. And that's the end about the random cluster model. Now what do I want to do? I want to introduce a new representation geometric representation that is going to allow me to tell you a little bit more when these conditions are satisfied or not. That's the next goal. Okay. Are there questions so far? No? Good. So the next representation is called the loop representation of the model. So I'm going to use a little bit of, the pictures. I'm sorry for people who are taking notes, but I don't draw sufficiently well to get all of this together. So chapter, or section, I don't know, 3, it's a loop representation. So first thing, is is there something to point or to? No. Okay, I will point with that. So you see the square lattice there. Okay. You see the dual lattice. So what we are going to do, we are going to work on another lattice, which is a medial lattice. So what is a medial lattice? At every center of edges, you put a vertex of this medial lattice, and then you connect the nearest neighbors together. So you get a rotated and rescaled version of the square lattice. So this is going to be the medial lattice Z2 diamond like that. So that's medial lattice. Now, let's imagine we have a percolation configuration, a random cluster configuration on my primal lattice. And let's assume I draw at the same time the dual configuration. So I would obtain something like that. Okay? Every edge which was open, closed for the original lattice, here, is now dual open in the configuration, and vice versa. This one was open, so this one is dual closed. Right? So I get together a configuration of a dual and a primal configuration. Now what I can do is I can draw loops going around these primal and dual clusters as follows. So imagine that I take a diamond in my, a face of my medial lattice. No, sorry. Imagine I take a place like that surrounding a vertex. What I can do, I can draw two arcs like that in such a way that I don't intersect either the primal or the dual edge, which is in the middle of my face. So imagine I have something like that. I can draw things. I would draw a loop like that, and imagine it is like that. Then I would draw like that. Okay, so when I draw all these loops together, all these arcs together, I get a family of loops, which are basically the interfaces between the primal and the dual graphs. Okay? So you see, for instance, here I forgot, but let's, here you have a trivial loop, here a trivial loop, and so on. Okay, so every time you turn in such a way that you don't intersect the primal or the dual configuration. Then you can just forget about the primal and the dual configuration. By the way, you can reconstruct very easily where they are. There is nothing hidden there. And you get a loop configuration, which I will call omega bar. Okay, so this is the loop representation of the random cluster model. Okay, so let's go up again. And let's carry on. So what is the first property I want to describe about this loop configuration is to tell you a little bit about the law of this thing. So imagine I set x, which is x of p and q, to be equal to p divided by 1 minus p times square root of q. Okay? Then the following property is saying how I can compute the law of omega bar. So for every p in 0, 1, every q positive and every g, maybe here let's take omega, a simply connected, just I want to be certain, a simply connected graph. So what do I mean by that? It's a finite graph which is connected and whose complement is connected. So there are no holes in my graph. Okay? Then, if I look at the law at P, Q, G, and here I will take zero boundary condition, the law of omega bar, yeah, maybe I should have said, if you don't fix the boundary conditions, then on the boundary maybe you don't close loops. Okay? Maybe on the boundary it doesn't close. So what you can do, what I will do just to simplify, I will take 3 boundary conditions, which you can see as simply closing all the edges outside my box, outside my graph. And if you close all the edges outside your graph, you see that you really get a loop configuration. The things really close. Okay? So this property is saying the law of omega bar is going to be simply, so there are going to be a renormalizing factor. And here I'm going to get x to the number of open edges, square root of q to the number of loops in my configuration omega bar. So you can express the probability of the configuration in terms of the number of open edges of the original configuration times square root of q to the number of loops. And notice one thing, which is that for P equal PC, if I put square root of q over 1 plus square root of q here, well, you can check easily what you get is 1. So in this case, x of PCQ is simply 1, and I get that the probability of a configuration is simply proportional to square root of q to the number of loops. So in this context, you don't even need to remember the number of open edges of the original lattice, of the original configuration. You just get square root of q to the number of loops. So let me just tell you a little bit about the proof. It's in fact very simple, once again. If I look at P to the number of open edges, 1 minus P to the number of closed edges, Q to the number of clusters, okay? Well, this thing I can rewrite it as what? I can rewrite it as, so let me just check exactly, 1 minus P to the number of edges in omega, square root of Q to the number of vertices in omega. And then what I will get x to the number of open edges and square root of q to the number, so square root of q to the twice the number of clusters plus the number of open edges minus the number of vertices in omega. So you can just check what I did is I multiplied by this. So if you divide here by this quantity, you will get p over p divided by 1 minus p to the number of open edges. So if you divide by square root of q to the number of open edges, you get x to the number of open edges. And you have to multiply by square root of q to the number of open edges. And then the q to the number of clusters, you find it here. And the square root of q to the number of vertices, I added it, I multiplied it here and divided it here. Okay, so here that was just a trivial manipulation. But now, if you think about it, this quantity, you can easily see by induction, say on the number of open edges, you can easily see that this is exactly the number of loops in omega bar. Just check for, say, 0 open edges. In this case, the number of clusters is equal to the number of vertices, so you get the number of vertices, and this is exactly the number of loops. And after you check that every time you open an edge, either you add a vertex, you add a loop, but in such case, you reduce the number of clusters. And just do the manipulation, and you see that it works. It's a trivial induction on the number of open edges. Okay, so that's the law of the number of loops, and I will be focusing on the P equal PC because that's where I want to work at the critical point. So just think, in this case, it's just proportional to square root of Q to the number of loops. Before I use this to prove a few theorems, I would like to tell you why it's natural to consider this loop configuration, where it came from. So it was inspired by physics, I mean introduced even in physics, for the following reason, is that in fact you have a connection, a property. If I look at the free energy of the Potts model at temperature beta C and Q. So remember the free energy of a model, you take the partition function, say on a box of size n, you take the logarithm, you divide by the size of your box, and you let this go to infinity, the size of the box go to infinity. It gives you the free energy of the model. For those who really don't know that, you can just forget about this property. It's not going to be used later. For those who understand, so this thing, in fact, well, the partition function of the Potts model, we saw that we could relate it to the partition function of the random cluster model. And you can fairly easily believe that, well, this relation allows you also to relate, I mean, basically this proof allows you to relate this quantity, which is kind of the partition function for the loop model, with the partition function for the random cluster model. So this partition function for the loop model is related to the partition function for the Potts model. And in fact, this partition function, I'm going to tell you in 2 seconds, is related to the partition function of yet another model. And basically, you get something like that, plus twice the partition function for what we call the 6-vertex model. I'm going to tell you what it is. And there are a few parameters for that. Where we have the following, that twice the cos of 2 pi sigma tilde is square root of Q. So what I'm saying is that there is a relation through this loop model. I'm going to tell you what the 6-vertex model is in 2 seconds, which is related to the free energy of the Potts model and the free energy of this model. Now this model, this 6-vertex model, has a lot of advantages. In particular, it's much more integrable than the Potts model itself. And in particular, you can compute the free energy via transfer matrix methods, so standard method in physics. So somehow this loop model is just, you get it by going from one model to another one, from the Potts model that you want to solve to this 6-vertex model, which is much more solvable. So let me just tell you what the 6-vertex model is. I mean, how you get from the loop model to the 6-vertex model. Well, for the loop model, what you can do is you can give an orientation to every loop, right? You could do that. And you will get configuration which looks like that, or maybe like that. I mean, configuration of oriented loops. Then you can just forget about the intersection, meaning this thing, you are going to say this is exactly like this thing. So here there is a loss of information a priori. Here there is none because if I give you that, you know how the two guys intersected. Okay, you know that this is the only way to reconstruct the thing. But if I start from this, you are going to get this configuration, which you don't know if it comes from this or from this. Okay, so I'm oriented every loop and forget about how they intersect. I get a configuration on my medial graph with 6 types of vertices. You have vertices like that, vertices like that, vertices like that, vertices like that. So all those are, all those are rotation of this one. Okay, so either it goes like that, like that, like that, or like that. And you have 2 others, which are like that, 2 in, 2 out, and 2 out, 2 in. Okay? Well, look at configuration like that. I will call them omega arrow, with only, around every vertex of the medial graph, I need to see that, and say that the probability of a configuration is proportional to some x1 to the number of patterns like that, x2 to the number of vertices like that, x3 to the number of vertices like that, x4 to the number of vertices like that, and x5, x6 to the number of vertices respectively like that and like that. Well, if you put x1 equal x2 equal x3 equal x4 equal 1, and x5 equal x6 equal 2 cos of sigma tilde pi, where you choose sigma tilde like that, you can check that, in fact, the mapping is, just between the two partition functions is giving you the same thing. The reason why is well, maybe I don't have time to discover. If you want, during the break, you can come and ask me, and I will explain to you. But there is this mapping. So now, so you have a mapping between the pods and the 6-vertex model. This model is very much integrable, so you can compute this quantity very well for you. The only problem is that if you want to have thermodynamical quantities of this model, you need to differentiate the free energy. Okay, so thermodynamical quantities are obtained by differentiating the free energy. The problem is that you have this connection only at beta critical. So you don't get to differentiate this. Even if you compute this fairly well, you cannot really differentiate. So this correspondence, unfortunately, doesn't give you all, everything you want. But if you assume a few nice things, and if you do a leap of faith, then you can at least try to guess how the phase transition goes. And the following is a conjecture by Baxter using this type of ideas, who proves, conjectures the following thing. For Q smaller or equal to 4, the phase transition is continuous. So in particular, the 5 conditions that I described in my theorem are satisfied. And for Q strictly bigger than 4, you have discontinuity in the phase transition. So in this case, none of the conditions are satisfied. And that's a conjecture that we would like to solve. Okay, so there is something strange with these 4 colors. Q equal 4 is the difference. The discontinuity. And so far, what we know how to prove, and what I will present in the next hour and a half, say, is that we know how to prove the continuity in this context, and we know how to prove the discontinuity when Q is very, very large. There are strong indications that we should be able to prove it for every Q bigger than 4, but still evading us a little bit. Okay. So that was the definition of the loop configuration. Is it clear for everybody, this loop representation, how it's obtained? So now I'm going to try to prove to you I'm going to try to prove to you that for Q very large, it's discontinuous. Okay? So this is known for a very long time, but the proof I'm going to present, I never saw it anywhere else, and I think it's short. So it's not the most efficient one, but it's short. So second section, discontinuity. For Q very big. And the theorem is going to be the following. For Q larger or equal to 6, 5, 6, 1. So in fact, the best thing you can get is 25. So I'm really, really far from optimal. But first, the proof itself can give you much more than that. But anyway, 25, 6,000, same thing. The phase transition is discontinuous. Okay, so apparently it doesn't want to come back. Hello. Ah. So it was efficient to speak to it. Okay. So I'm going to just write on the bottom. So it's going to be approved by pictures, right? Because it's going to be sufficient. I hope it's going to be sufficiently convincing. So what do we need to do? So we need to prove one of the conditions in our theorem. And what we are going to do, we are going to prove that when I take the wired boundary conditions, I have an infinite cluster almost surely. So what I'm going to do, I'm going to work with the free boundary conditions. I'm going to take, say, a loop. So take L, a loop, surrounding, I'm sorry, we won't see very well, but surrounding the origin. So you fix a loop surrounding the origin. And let's denote AL to be the event that L is a loop of omega. So I consider all the configurations that have L as a loop. So I fix the loop. The loop is really fixed. So let's say this is the loop I fix. And I only look at configuration with this loop in. My goal is to prove that the probability of this event is very small. Okay? And how am I going to do that? I'm going to construct a mapping from this AL. So I will call it SL. So from the set AL to the set of loop configurations. And I'm going to construct this mapping in such a way that it's one-to-one, but in such a way also that the image of every element here has much bigger probability. Because if I can do that, if I can construct this one-to-one map with the image of every element here having a very big probability, what does it mean? It means that the probability of this event has to be very small, because the total mass of my measure is 1 anyway. So how do I do this mapping? So what I do is the following. I look at my loop, and I choose, to start with, I choose, you see, one direction in such a way that, so my loop is going through 4 types of edges, right? These edges, these 4 types of edges. So there is one of these types which is used more than a quarter of the time. So choose one of these directions. So say in this case, it's going to be this one. Okay? So you choose it before. So you have your loop, you choose, okay, I go more than 1/4 of the time in that direction, I choose this direction. And so now what you are going to do, you are going to first erase the loop. So you take a configuration omega in your set, you erase the loop from this configuration. You take the configuration inside your loop. Okay, before you had this thing, it was surrounding a family of loops. And you just shift it away from this guy. So if you took this thing, you'd shift it that way. If you would have taken this, you shift it that way, this that way, or this that way. Okay, you shift by one thing somehow. So it gives you still a loop configuration. But now you see you have many faces which are just not surrounded, not intersecting any loop anymore. How many of such faces? Well, all the faces that were, intersecting my big original loop in that direction. So if you go back, you had this thing. Look at all the, sorry, maybe that was this one that I chose. Look at all the faces that are intersecting an edge going like that in this loop. You erase, you shift, and now all these faces, they are free of any loop. So what can I do? I can just put trivial loops in these faces. Okay? So you started from a loop configuration. You do your manipulation. You end up with another loop configuration. Notice that it's a one-to-one mapping. I know the loop L. I know where it was. So I can reconstruct trivially the thing. Now, what is the probability at PCQ of my loop, the image of omega? And let's say if I divide by PCQ, so there is 0 here, of omega, if I compare the two configurations. Well, the difference is just going to be square root of Q to the number of loops in SL of omega, it's omega bar, sorry, minus L of omega bar. Okay, it's a difference, it's square root of Q to the difference between the number of loops in my image and the number of loops in my original thing. But what is this difference? So I remove the loop, and then I added trivial loops for every of these faces. So the number of loops here minus the number of loops here is just the number of these faces minus 1. But the number of faces is the number of edges like that. That's what I told you. So that means that it's at least the length of my configuration of my loop L minus 1. So this is always smaller or equal to square root of Q to the length of L divided by 4 minus 1. Okay? Well, we are almost done, because now what we can say is then if I look at the event AL, so it's the sum over omega in AL of phi 0 PCQ of omega. So this is smaller or equal to the sum over SL of AL of, or maybe omega in AL of square root of Q to the minus the length divided by 4 plus 1 times phi 0 PCQ of SL of omega. And now this factor goes away, and the sum here, since the map is 1 to 1, the sum here is smaller or equal to 1. Yes?
I'm just a bit confused. The inequality doesn't go in the other way. You say you wanted
Yes. So here it goes. Yes. So here it goes in the right way. So this thing, I mean, you add. I mean, what is the difference? It's exactly the number of edges like that minus 1, and I took this direction to be in such a way that I have more than a fourth of the length. So you want this thing to be much bigger than this. Sorry. This was the other way. Yes. Sorry. So I get that. So this is smaller than square root of Q to minus the length divided by 4 plus 1. Okay? Very well. How many faces, how many loops do I have that are surrounding like that the origin of length L? Well, I have more or less than, so every loop, every single time has 2 choices or 3 choices. Why did I put 2? 3. Well, 2 choices. So the number of loops surrounding the origin is smaller than 2 to the number to their length. The number of loops of this length is smaller than 2 to the length. So now, if I take square root of Q to the 1/4 to be strictly bigger than 2, what do I get? I will get by Borel-Cantelli that the number of loops surrounding the origin is finite, almost surely. Right? But if I have that, what does it mean? Well, you can check easily. That means that there is a dual cluster which is infinite. That's the only way. If you have only finitely many loops surrounding the origin, you can check that there is an infinite cluster in the dual. But the dual of the free boundary condition is a wired boundary condition, so that means that there is an infinite cluster in the primal model for the wired boundary conditions. And so this will happen as soon as Q to the 1/8 is bigger than 2, which gives you not that, because I said 3 earlier. I don't know why I put 3. But if you bound even more stupidly the number of loops by 3 to the number of to the length, you get exactly your 65, 61. Okay, so for Q very large, it's very, it's kind of very simple to exclude, to prove that none of the conditions are satisfied and that the phase transition is discontinuous. So it's exactly 11. So we are going to do 5 minutes break. And then in the second part, I will try to convince you that for q smaller or equal to 4, the phase transition is continuous this time. Okay? Very well.